Good morning, everybody. I hope you are doing well. We are going to have a short little podcast here on bases. And the nice thing about this is that if you really understand the acidic side of things, we can just flip to the base side. So you can see that I have the definition here for the Arrhenius and Bronsted-Lowry, and we are still focusing on the proton acceptors for Bronsted-Lowry, just a little more generalized definition of bases. For strong bases, the alkali and alkaline families, so I hope you're thinking of family 1 and family 2, depending upon their dissociation is going to be influenced, this should say, by solubility, and family 1 is a lot more soluble than family 2. So you need to keep that in mind as you're looking through some of these equations. Now, speaking of the equation, I should have left you some room right here. So let's just write down first the general basic equation. And we would say categorize our base, and when we write the base equation, we always are going to add water because we need to see that source of the hydroxide ion. And remember, bases are proton acceptors, so you can see this base here on the right hand side that has accepted the hydrogen ion, which is that acceptor. We can still do the same thing and bracket our substances together in our generic equation, and then we can find that B actually is our base. And then if we look at what has happened, our base's definition is a proton acceptor, and yes, it's accept something. So this would be the conjugate acid and has acidic properties, which should make sense to you because of this hydrogen ion here. It would be able to donate that. And acids are proton donors, so the water over here is donating a proton to that conjugate acid, and then that makes my hydroxide a conjugate base. So let's go ahead and answer now this question that we have up here where it says calculate, so I'm up here, calculate the pH and the percent ionization for 15 molar nitric acid, or no, 15 molar ammonia, sorry. And then we have the Kb that's written there. You can see that the Kb is incredibly small, so we are going to be able to drop an X when we do our ice expression. So we would see that we would have NH3, which is our base, as you can look at above. I will add my water as we just did in our general equation. And that ammonium is going to be a proton acceptor, so it's going to make ammonium, ammonia to ammonium, plus my hydroxide. And if I write down my initial concentrations, so the concentration here was 15, was the molarity. And we don't have to worry about the water because we're not going to put that in our equilibrium expression, just like we did similarly with acids. So because that is not built up yet, this is going to decrease by x, increase by x, increase by x. And then I can go ahead and write my expressions. So 15 minus x, and then I have x and x. And if I put it into my Kb, now we were doing Kas because they were acids. Ammonia is a base, so the Kb is equal to our product over reactant, the concentration of our product over the concentration of our reactant is equal to our Ka. So that is going to be x squared over 15, and I can drop that x because my Ka is smaller than 10 to the negative third. So nothing new that we are doing versus the acids. The bases are exactly the same. It's just the opposite in nature. 1.6 times 10 to the negative second is going to equal our hydroxide ion. So this is where you have to be careful because it's asking for our pH and the percent ionization. So for pH, we have to make sure that we convert our OH into the hydrogen ion so that we can see what the pH is. So I'm going to take my POH and I'm going to take the negative log of 1.6 times 10 to the negative second, and that pH is going to be 1.80. I have two significant figures here in my concentration, so I need 2 decimal places here. And then I can take that my pH then is equal to 14.00 minus the 1.8, and I'm going to get 12.20 is going to be actually my pH, which is going to show that it is indeed a basic solution. And then if I want to do my percent ionization, remember it's part over the total. So it's going to be my part of the hydroxide that has ionized over the initial concentration, which was 15, change it into a percent, and I got 0.11% that is dissociating. Okay, so this is very small Ka, so that shows you that it should basically be a product, or reactant, sorry, stay on the reactant side, and because of the amount of dissociation, you can see that indeed to be true. Okay, our last page just has a lot of trends. I'm not going to sit here and read all of this for you, but you should pay attention and look at some of them. Sorry, here we go. And when comparing different weak acids, acid has a greater value for Ka, stronger acid. Go through and read all of these. Solution has the same pH. What's going to happen? I do have a typo here on the second one where we have our K is greater than 1, K is less than 1. Hopefully you're getting more and more comfortable with that now. This should say the HX as reference to this. I'm not sure where I got that S from. It's a stronger acid, and then the anion, or the Y to the -1 value, is the stronger base. Make sure you highlight those, go through and read those. One thing, we have some more trends to explain acids. A lot of this stuff I have talked about, so make sure you read all of these points. One thing I do want to call your attention to is that this trend right here is for family. Okay, we're going down the family, fluorine, chlorine, bromine, and then this should be iodine down here. And if you look at the relative bond strength, you can see that it is also decreasing as it is going down, and the radii is increasing. So again, those are some periodic trends that we know about that we can talk about. And again, we know that if this has a very small bond strength, this one is going to be easy to break that hydrogen apart. So this is going to make this a stronger acid. The other thing I want to call your attention to here, so this was in a family, and then the last point down here is within a period. So going across the chart, we have to take a look at our electronegativity. And here we're talking about fluorine. Again, this is another typo. This should be the acid HF. And the comment is talking about versus water. I hope that you would recognize that fluorine is more electronegative than the oxygen, and so that there's going to be a stronger bond there, weaker acid versus the water. That is amphoteric and can act as an acid or a base. So really this page is just a summary for you. Make sure that you feel comfortable with that, especially when we start looking at the multiple choice section for this test in a couple of weeks. You guys have an awesome day and an awesome break. I know a lot of you are heading out on spring break, so enjoy your time and come back rested and ready to go. I will see you soon in class. Have a great day.